Let's do a very quick review on the composite pattern. Because the main goal for today, we're going to finish the composite pattern, and then we have to extend the composite pattern to solve another extended problem. Okay, they are related, which is called visitor. Okay, we'll get there. So now, what I would like to remind you about, so what kind of problem are we trying to solve for the composite pattern, which we talked about last time? You have application like this. You got composite components like a cabinet, which contains subcomponents. And each subcomponent may be further recursive, like another chassis and chassis over here. And it might also be a base components, like a power supply, which cannot contain any further components. Okay, that's kind of the problem we are solving. It doesn't have to be exactly this manufacturing problem here. We'll see another new one when we talk about visitor, but similar kind of problem. So the challenge really is, how can you handle both the base and recursive cases? So in some way, we are defining a recursive solution to this problem, like what you learned from your previous programming courses. They're related. Okay, how do we solve this? Let me go to the composite pattern right away. So that's the architecture for the composite pattern, which makes use of multiple inheritance. Okay, let's have a quick look, and then we'll review how things can be run at the runtime, which will be also beneficial for the visitor pattern today. Okay, so now again, what we have is over here, we have the client code over here, the main program, and then we have a client-supplier relation over here, and then we have our equipments over here. So that's deferred, which means everything that we are trying to deal with is a kind of equipments. But there are two kinds of equipments. Either the base equipments, which are direct descendants of the equipments, which is card and disk drive. So these are the base cases. I'll say base, which means they cannot contain any subcomponents under them. On the other hand, we also got another class called composite components. So this is really the key. For example, we have cabinets, we have chassis, we also got bus. So these are three example composite components. So what's really interesting about this is, at the design level, we do support multiple inheritance in IFO. So this is one parents for composite equipments, which means composite equipments like cabinets, chassis, and bus, they're also a kind of equipments. So that's what this inheritance relation is telling you. On the other hand, they also tell you the composite equipment is also a kind of composite. Okay? So what is really a composite? A composite supports two general features. So one is called children, which is just going to be a list of whatever type you have. So it's generic, okay? Which means we try to make that as general as possible. And also, for any composite, you can add a particular child to it. We'll see example in just a moment. So these are the two general features. Of course, for your particular design, you can add more features if you like. And one more thing to mention, so these are the two inheritance relations that are important to see. Also, there's also a client-supplier relation over here. Okay? So what does that mean? So when you have something over here, you can see we have children, which means the feature name. So that means composite equipment contains a feature called children. And what's the type? The type is simply a list or like an aggregation of certain things. And the ... over here simply refer to the supplier type. Okay, we just that's how we abbreviate the notation. Okay, again, you should really know how to understand the diagram over here. ... simply supplier type. Okay, that's about the architecture. Okay, any questions about this? Yes.
I just want a quick question about the composite class.
Sure.
Is it native to IFO, like it's free for you to use, or is it something?
Oh, composite, I would say you have to define by yourself. Oh. Yes. So the question was, the composite class, was it supporting IFO library? No. You just can easily define that. Okay. Yeah.
Why, like on the arrow from composite equipment illustration?
Sure.
Why does children go there and not from composite equipment?
Oh, that's because, okay, good question. The question was mainly about this arrow over here. Let's clarify. The question was about this arrow over here. First of all, let's think it this way. You can think about the composite equipment has certain feature that's inherited from its ancestor class. For example, one of them is the children. Okay, so let's see one code I want to show you. if you go to the code for composite equipments over here, you can see inherits the equipments. It also inherits the composite, in which case we instantiate the T over here by equipments. Okay? Accordingly, that means this particular feature that's called children over here, when it gets inherited to the composite equipments, since we already instantiate T by equipments, it's as if we were trying to declare the following, to say children over here is of type linked list of equipments. So far so good? Right? That's how we instantiate birthday book, for example, previously. Okay, so now let's go back to here. So now we know that composite equipments implicitly actually declare this children, which is of type linked list of equipments. So that's a client supplier. So that means children, So that means composite equipment is the clients. So who's the supplier? It's basically like a linked list of equipments, but it's more important in this case to show the equipments. Okay, so we are saying that we simply got a linked list or list of ... Over here is the supplier for the composite equipment, which is equipments. Okay, guys, are we okay with the green client supplier arrow? If you have confusion, let me know. Okay.
So Professor, is the only point for the component class being like, kind of this multi-inheritance thing that it's going through, is the only point that those classes that are like, kind of inheriting from the composite equipment, they're the only ones who get to use that method?
Correct. So the question was, in this particular example over here, as we briefly touched last time, let me say that again. You can think about currently all these classes over here, let me try to circle them together in pink. So this is a particular cluster. Let me say that's a cluster called manufacturing. Okay, it's a cluster. Okay, all these classes are related to the problem you're trying to solve for the equipments. However, the composite ideally should not be included as part of it. Let's say we're going to introduce another problem which is also going to instantiate the composite design pattern, which we'll do today. It's, let's say we're going to solve a problem for expression language, which is a completely different problem. However, for that particular problem there, we can still reuse this particular composite class. Right? Yeah. Okay, good. Any other questions about this composite? Yeah.
So Professor, how would you do the same composite pattern design in like languages that don't support multiple inheritance, like for instance Java?
In Java, what you have to do, unfortunately, you may have to either put the children, let's say in the Java case, you cannot extend for multiple classes, right? In that case, either you have to make composite maybe an interface, in which case you can implement from that, but you have to implement the methods inside the composite equipments class. That's one approach. The other approach would be you simply get rid of this class, let's say in Java. You don't have this class. However, put all the code directly under here. But I would say the first approach using interface will be better. That means everyone who wants to instantiate the composite pattern, they will always have to implement the signature for the composite. Okay, so you got unified signature. Okay, good. Okay, any other questions? Okay, so one more thing to mention. So the good thing about this particular design is, so now if we try to do disk over here, D is of type disk dot add, and then card, it would not be allowed by the compiler because add is only a feature that belongs to the composite descendants, right? But card and other things, they are simply not. Okay, one more thing to show about composite pattern, which I did kind of in a rush, but let's try. So let's say this is what we want. Let's say in the case of the equipment class, which is at the top of the hierarchy over here, I define a feature called price over here, okay? And now what we got to think about is the price is somehow going to be inherited to both the base equipments and composite equipments. But the way we implement the same price feature will be different. And this is according to the uniform access principle. From the client's point of view, they can simply say whatever equipment I have, that price. They don't have to worry about for the supplier how they implement the price feature. It can be by storage using attributes, or it can be by computation using a query. Okay? More precisely, you can see in the case of the base equipments over here, you can see the card is simply descendants of equipment. So that's the base equipments. In this case, price is simply just a attribute. That's why we can do the assignments over here. Okay. By the way, the source code is available on the web, so you can also download it and play with it. So this is attributes. On the other hand, the same price feature, when it is inherited to the composite components, we don't really have a default price for any composite component. We simply don't know how many subsystems you might contain for each composite component. So what we have is something like this. How about green? So composite components is over here, and now for the price feature over here, it's implemented as a query, which means we have to run through some code over here to see its effects. So what do we do over here? What we do is we simply go across the children of this particular composite components, and for each children, we simply call their price. So now this price, again, you can think about when we are calling this particular line over here, you want to think about the uniform access principle, which means if the current child is a base component, that means it's by attributes. Otherwise, if it is a composite component, it will be by computation. Otherwise, computation. But we'll see one example. Okay, so that single green highlight over there is the most important part to understand. Because for the equipment over here, we simply don't know whether this particular one is actually composite or base. Depends. Okay, now let's have a look at how we can trace this block of code, which I did very briefly last time. Let's do it again, because this will be also very useful when we talk about the visitor pattern. Okay, let's try over here. Let's say I'm trying to basically declaring car and drive being basic equipments. We got cabinets, we got chassis, and we got cabinets, chassis, and also bus, right? We got these variables. Let's try to see. The first line over here, when we say bus, so we are basically creating a bus object over here, and then we are trying to add a card, right? That's what we're trying to do. So the car over here was created over here. Okay, the car was created over here, and this is the car objects over here that we have created, and with a price 200. Okay, so when we say add the car to the bus, that simply means the first elements in the children list of the bus is now going to point to this particular car. Okay, you can see the arrow over here. Okay, that's how we make the link at the runtime. Okay, and other links will just be set in a similar way. Let's do that quickly. Okay, other than that, there's a blue link that I just put over here. Let's put another orange one. What does it really mean when we say chassis.add bus? So this is the object that we're talking about, chassis over here, and we say add the first child to be the bus. That means this is the first child, and what we wanted to point to the bus. That's why it's pointing to here. And the second one over here, we're going to add a second child for the chassis to be the drive. And the drive object was created previously over here. Right? That was created over here. And then, so the second child is going to point to over here. So these are the two children for the chassis. Finally, we are trying to build, as you can see, the way we try to build up things will be bottom up. Okay? And then we got cabinets. Let me use pink. So we got cabinets over here and add chassis. That's easy. Just the first child for cabinets will be pointing to this particular objects. Okay? That's only the first stage. We're trying to build a tree structure. Okay? So now what we want to figure out is we want to know what's the worth of this particular cabinets. What's its worth? Well, that's exactly what this line is trying to say. Cabinets, the price. Basically, that's something we want to figure out. But this involves quite a bit of detouring at the runtime. Let's see exactly how it is going to be done. Okay? So now when we first call this cabinets a price, so now we got two versions of the price. Okay? Let me show you which two versions we have. Either we have a price from here, which is simply just the attributes for the basic equipments. Or we have the price, second version, which is from the composite equipments. Okay? When we try to call this particular line over here, which version are we calling? Are we calling the version from cart, for example, or equipments, right? Or are we trying to call the version from composite equipments? The question is, when we are trying to do this line over here, when it's a cabinets, the price, which version of the price are we calling? The one above or the one below? Well, if you want to know which version is calling, it's about dynamic binding, right? So you want to figure out what's the dynamic type. Okay? The dynamic type over here, let me just annotate for you. So you can see the cabinets over here, the dynamic type is basically cabinets, right? Right? To actually show you the highlight here, you can see the cabinets was declared over here, and this is how we created the cabinets. Remember, when there's no curly brackets showing here, that means it's the dynamic type just the same as static type. Okay, that's what we said before. So now, because the dynamic type is cabinets, that means the version for cabinets will be used, and that version is simply inherited from composite equipments, right? So that means this version is going to be called. All right, let's call that version then. If this version is going to be called, so we're going to go across the children of this particular cabinets, which contains this particular list over here, right? Just one child. And now, when we say result, which initially is 0, because that's a real number. When we say cursor.item.price, okay? Now, cursor.item refers to which objects in this case? The orange chassis object, right? Over there, okay? Let me just show you, okay? For now, over here, you can see that when we try to go across this particular list, the first iteration is going to refer to this particular chassis objects over here, right? Because of, from this previous build-up, right? That's how we build up the tree structure. Well, you can see that over here, when we say, you can see the pink line over here, right? That's how we build. So that's why I'm drawing the diagram to show you, visualize the tree structure. So now for the first iteration for this particular cabinets, the child is going to be referring to the chassis objects over here, right? So that means we're going to refer to this object here. And then when we say cursor.item.price, is it going to call a query or going to call an attributes? Well, simply because chassis object over here is just another composite, which means it's two children. Agree? Okay? And then that means we're going to go into this price again. Right? So that means over here, we're going to in turn call chassis dot price in turn. Okay? So we started with cabinets dot price. In turn, we have to call chassis dot price. Okay? And now, for the how many iterations are we going to run to call this price in order to figure out? 2 or 3? Well, don't guess.
Like the final one?
For the chassis over here. Yeah. So I'm just saying for this particular chassis, that'll be just 2, right? Because we got size of the children will be 2. Okay, let's go to the very first iteration. When we go to the very first iteration there, we're going to have the same line. Cursor.item is now going to refer to the bus objects here, right? According to the tree structure. And now, for that particular one, we're going to figure out its price. To figure out its price, we have to, again, call some version of the price. Which version are we going to call? The composite, right? Because the bus itself is also of type composite, right? Bus is the composite equipment, right? So let's go back there. So that means we're also going to call bus.price. Now, in order to call that, we have to go, again, the across loop once more, right? You can see so many times, right? So now, in order to call bus.price, how many iterations are we going to run for this particular bus? Just 1, because size of the children is 1. And then we go there for the first iteration, and we'll see again this line here. Cursor.item is now referring to this card objects over here. And now we have to call which version of the price? The equipment, right? It's going to be attribute, because now we're gonna say in turn, we're gonna say, I'll put it here, card dot price. In this case, card dot price is going to be, well, just going to be whatever price it is, right? It's a basic equipment. In this case, that will just give us 200. Okay, so card dot price will give us 200, and then bus dot price, the first child is going to be 200. That means overall is 200. And then the price for the bus will be 200. And now let's go back to the chassis. It's like a stack trace, right? That's how we trace recursion back before. And then chassis price will be 200 plus whatever the worth for the second child will be. What's the second child for this particular chassis? 500. Well, true. That's simply referring to this particular drive, right? And that means we also have to call drive.price. And again, which version are we calling? Attributes, right? The equipment's version, right? Basically, from the diagram, as long as the equipment itself does not have any children list, that means the attributes. Otherwise, you can figure out it recursively. Okay, so that one is going to be 500. So that means the chassis price will be 200 plus 500. That will be 700. And finally, the cabinet price will be just 700. Okay, guys, are we okay? It's still a little bit fast, but hopefully it's better than last time. Okay, so please make sure you understand how things will run recursively. We'll see exactly something similar in the visitor pattern with some extra complication. Okay, any questions about this? Yes. Okay, if you see the architecture over here, you can see that, as we said before in the architecture, there is a class called equipments. There's also a subclass of that, which is the composite equipments, right? So you can think about all the base equipment is at the first level of the children, and all the composite equipment is at the second level, right? Yeah, good. Yeah, so car and disk drive, they are both bases. All right. So these are just the recursive, which means you can add recursively, right? Good. So basically, we're building a tree. Okay. Alrighty. Let's now go to our new pattern. We're going to build on top, so everything's going to be related. Motivating problem. Okay. Now it's time for you to practice a little bit. Okay. Now, this is a problem. Based on the composite pattern we just learned, we just review. Now, how do you model the structure? I want to design certain classes to model expressions like this. I may have a number 341 or number 2, and also I may also support addition. The addition is going to, what can be the operand? You can see the plus over here has 2 operands over here, right? In this case, I simply put some very simple operand for you, simply 2 numbers. It could have been something like this. I'll show it to you on the iPad. To show you the problem itself is indeed recursive. Okay, so now let's say this. If I have an addition over here, I'm expecting something on the left, something on the right. The left-hand side, it can be either a number like this, or it can be just another addition. Maybe 2 plus 3. And over here, it can be addition over here, and the left-hand side can just be another addition here. So maybe 4 plus 7, and here can be just 9, for example, right? That's kind of the expression we are building up, recursive. Okay? Let's assume we only got integer numbers, integer constants, and we only got addition to build up things more complicated stuff. Now, why don't you take just 1 minute or so, take this opportunity to draw some diagram on your paper, and then I'll show you something, and we'll go from there. And I'll let you cheat. Try. You know, it's a good opportunity to try. Okay, just 1 minute.
What kind of diagram?
Bound diagram. Just show the architecture. You don't need to worry about contracts. Okay? Just worry about the architecture. So what classes do you have to create? And think about this diagram. It's just another instantiation of the composite pattern. Okay. However, this one single class you don't have to implement anymore, which is the composite. The composite is completely generic, which means you can reuse it for this particular one. Okay. I'll draw something on the iPad, and then you take 1 minute, and then I'll. You know what? Let's talk about it a little bit later. Yeah, because otherwise it will be distracted for the flow. The structure should be very similar. Okay. Meanwhile, let's try to do something together very quickly. Let's think in this way. I have basically 2 clusters. I have one cluster over here. I got another cluster over here. Okay? I got two cluster over here. Okay, 2 clusters. Let's say this cluster, first one is manufacturing. And another one is going to be expression, let's call. This one we have already seen, and this one is something we're going to create. Okay? I'm going to show you basically back to your original question, how can we reuse the composite? I'll show you right now. Okay? Let's review the manufacturing very quickly. So we have some main program over there, and then we have a client-supplier relation over there, and then we have equipments, which is deferred, and also under equipment, we got a base equipment. Let me just say one of them, just card, for example. And then at the, okay, that should be effective, of course. Under the equipment, we also got another class over here, which is a composite equipments, right? That's what we had before. Under composite equipment, we got things like cabinets. Okay, so far so good. And then remember this, we're missing one inherit. Oh, and also remember for the composite equipments, we also got something like this, right? This is going to be a list of equipments. Am I missing something here? Some inheritance, right? I'm missing an inheritance. You know what? To make the diagram look a little bit nicer, what I will do, I'll move this down a little bit, and let's try to do this. I'm going to have some inheritance over here. So this is going to inherit from some class called composite, which is generic. That's what we had, right? Now, let's try to introduce our second instantiation of the same composite pattern. And then we can reuse whatever the composite is. One more detail to mention, okay? Which is more about implementation. Remember, for this composite equipment over here, when we try to inherit from the composite, we have to instantiate the T, right? We didn't really make the composite equipment itself generic. We make it not generic. So one thing to mention here, this is basically composite of equipments. Okay, something to mention. You can see also the code. You can imagine that for the case of the expression composite pattern, we're going to instantiate T by something that's different. Okay? Let's try. Let's try the following. Let me use green. So now we may still have another main I'll say main number 2, just another client program for the expression. And basically the same structure. And then it's going to be a client of, now it's not equipment anymore. Why don't we call it expression? Okay? Expression. Under expression, so now help me out. What should I have? What's the base case? The number, right? Okay, let me call it constant. Okay, or number, doesn't matter. Okay, let me say under this, I have something called constant. And that should be effective. Like that. And I should also create another, oh, of course, I need a class for addition, right? But the addition class should not be a direct child of the expression, right? It should be a composite. So why don't we create another expression, another class over here? Let's call that maybe composite expression. Composite expression. Okay, that should be deferred. Okay, that should be a direct descendant of that. And also under that, we should have something called addition. Now you can see why I said it's just another instantiation for the pattern, right? Basically the same architecture with different names. Of course, different implementation as well. Okay, and we also need this client-supplier relation possibly. Now, have a little question for you. If I say, it's a very important question, so I'm going to use a different color. If I say this is going to be a list of expression, right? If I say that, okay? Of course, that means also this class should also be a descendant of the composite. That means when we try to instantiate a T, T should be instantiated by expression, right? So now I want you to focus on this particular line over here. Do you think using a list in general is a good choice? If you don't think that's a good choice, why not? What can go wrong? I'll give you a little bit, yeah, go ahead. You have to parse it? No, nothing to do with that. I'll give you, yeah, say something, and then I'll give you hints.
Yeah, so the list, you wouldn't know exactly which part of the list you were in?
Well, I can use index, right? You can say, I want to go to index number 1, I want to go to index number 2. That's not a problem. You're getting somewhere. I'll give you, you want to say something? Go ahead. All right. So I'll give you a little bit of hints. In the case of the composite equipments over here, we are talking about a composite equipment that can contain as many sub-equipments as we like. That's why list is a good choice. On the other hand, for the composite expressions such as addition, do we have an arbitrary number of operands? How many do we have? How many operands? Not operator. How many operands? 2, right? Because a binary operation, right? So now in this case, using a list is dangerous unless you have invariants for that. What will be the invariant for that? The danger, first of all, without any invariant is to say, at the runtime, if you try to create an addition with 3 children, that's simply not right. Agree? So what kind of invariant can we add to this? Huh? Children.count will be true, right? Right? Remember, we actually got something like here. Remember, we got something called children, which is a list of T. And also, we got add child. Also, that one there, child is of type T, right? That's from the composite before. So now, if we really want to follow exactly this architecture over here, what we should do over here is to have invariants at this level. Let's assume we only got binary expression. You may want to say something like children dot count is exactly equal to 2. This is just a very nice place to illustrate how you can use invariants, right? Because now we are saying that in the case of the composite equipments over here, we do not need such invariants because we don't really restrict the number of equipments you might have as sub-equipments. On the other hand, for the case of the composite expression, we only consider binary expression, let's say. In that case, we do need this invariant here. Okay? Everybody follow? Okay? Yes?
I have a question, Professor. How can you actually do it without having an invariant?
I would say,
Another way.
if you don't have invariants, okay, you're saying what will be another way to do it,
Yeah.
which will be still safe and but without invariant, right? Let me say one more thing. That's a good question. That's exactly what I'm going to talk about. Even adding the invariants over here, let me ask you a question here. At the runtime, how do we do this? That means you're going to do something like this. If I say create, let's say I got something called add of type addition. And then I can say create, no, I don't have to say that. Create add dot make. Okay, I just initialize a new addition object over there. But now the question is, how do I add something to the left? How do I add something to the right? Before I let you answer, let me give you some context. I can also get another, maybe C1 and C2. Let's say they are of type constants. And then I got creates C1.make. Let's say there's a constructor, I can simply give maybe 2. I also say creates C2.make. That's another constant, maybe 3. So what I really want to try to build up is something like a 2 plus 3. So in this case, 2 is the left operand, 3 is the right operand. According to what I have got so far, how do I add a left child?
You should make the container generic. Instantiation by the tree.
Which container? Which list? You mean the list over here? It is generic. It is. Remember that's T. T is generic. The list itself is generic. Yes, we're just saying T, right? How do I build it? Well, in this case, let's say this. If I simply do the following, if I say C1.add, oh, sorry, not C1.add. Let me do it again. If I say, you know what? This name here can be confusing. What about I simply do another name? Can I just say A, standing for addition, okay? I can say A.add, right? Because A is of type addition, so I can call the add child. Add child over here, and then I'll say C1. A.add child, and then C2. If I try to do another one, A.add child, for example, I also got C3, let's say. What's going to happen? Invariant violation, right? Because after the first line, after this line here, a.children.count will be 1. After this line, a.children.count will be 2. After this line, a.children.count will be 3, which violates exactly this invariant here. So this is definitely not good. Okay, just keep it in mind. So this should not be there. Okay, I'll just cross that out. Yes. Somehow. But we haven't talked about evaluation yet. We're just talking about building the structure. Yeah. Okay, let me just go a little bit. Yeah. You can definitely play around with the design. Let's not go there just yet. Yeah, let me just stay with this design. I don't want things to get too complicated just yet. Okay. So now, let me just draw some diagram over here very quickly. So what we have over here after these two lines, okay, basically A is pointing to an addition object over here. And then we have attributes called children, which is going to be a list, right? And we know that the first element in the list is going to point to, depending on the chronological order that we add the C1 and C2. So that means this one here is going to point to some constant objects. And this second one is also going to point to a constant objects. And now the value for the first one should be C1's value, which will be 2. And the second one should be 3. And by the way, this should be C1, and this should be C2, right? That's kind of runtime structure. Now, adding them seems to be okay as long as we can keep track of the chronological order. However, now, how do I get a left expression? I want to get a left operand for A. What should I say? Would A.C1 even compile? Why not? If I only, I know. If I only look at A.C1, sorry for interrupting. If I only say A.C1, what's the static type for A? Addition. Does addition support any feature called C1? No. So this wouldn't even compile. So what should I say? A.children, getting there. A.children, and at position 1, right? Okay, following? Okay, that's how we get it left. How do we get it right? A.children at position 2, right? That's the left. and that's the right. That will work, but you can see that kind of inconvenient, right? That means every time we want to refer to left operand for addition, we're going to say a.children.1 and or a.children at position 2. You can have some wrapper query to do this, but it's back to your question, is it possible to do it in another way? Yeah, conceptually you have to make a.left, a.right, but left and right is not supported yet. Yeah, you can create a new class. That's kind of what I would like to do. So my point is, first of all, there are several quite many things illustrated in this slide over here. Let me summarize quickly. We have basically one instantiation here, and a second instantiation here for the same composite pattern. And they're trying to reuse the composite class over here. That's good. However, given the very special feature of this particular composite expression over here, which is binary, we can either create an invariant over here to say the count of the children should always be 2 to avoid trouble. But we found that the inconvenience would be when you want to get a particular child or operand for this particular addition, you got to say children at position 1 or children at position 2. To really save us from such trouble, what we can do instead is to get something very similar to composite pattern. It's all still a composite pattern. We're just going to play around with this composite over here a little bit. Okay? That's what I will start with. But still composite pattern. Okay? Do we any questions about this slide here? Okay? Hopefully that also answered many of your questions from last time. You were confused about how we can reuse the composite class. That's exactly how you can use it between the different instantiations.
Yes, that's a quick question. Is the expression class supposed to be inherited from composite, or is the composite expression class?
Well, remember only the, oh, good. Thank you so much. That was a very serious typo over there. Absolutely. So I think exactly what I meant to do. Thank you. So I should say inheritance should be from the composite expression. Thank you. That's good. Yeah. I think you guys thought the same way. We just didn't notice that. So we should really pay attention to the detail of the diagram, right? Imagine if I give you that as an exam question. You should tell me that it's pointing to the wrong class, right? Watch the recording. Yeah. Yeah. All right, guys, any questions?
Professor, just one quick question. This left diagram.
Yeah.
Were you creating a new class called Composite with?
You mean here? Oh, I just abbreviate that. So composite equipment is exactly what we got before. So this part here is exactly how we learned from last time, right? And we're just creating another instantiation with a composite pattern. Okay, good. Now, let's see a slightly different design for the composite. That's what I would like to show you. Like this. Okay, let's see over here. Okay, that's the composite pattern, composite-like pattern. Okay, does it make sense to you? Let's see. So what do we have over here? It's very similar to what I just drew on the iPad. So rather than having a generic composite over there with a list of children, I simply got left and right to make it much more convenient for us to refer to left operand or right operand for any binary operation. Okay? So now, given this design, how do we solve the original problem? Remember, the original problem was, how do we represent, for example, 341 plus 2? According to this architecture here, what should we do? Right? That's something we got to figure out very quickly, okay? Let's have some idea. Similar, let me just go over the architecture with you. So we got a class called expression over here, which is deferred. Also, we got a composite class here, also is deferred. And now under expression, it can be either a base case, which is constant, that is effective. And we can also have a class called addition. In that case, that's a recursive or composite, in where we're going to use multiple inheritance. Addition is going to inherit from both expression and composite. Now, in the case of composite, we simply say rather than a list of children, we just got left and right expression. Okay, makes sense. Good. Yeah. Okay, so now one thing to note. The value over here is very similar to the price that we talked about in the previous example, right? However, we're going to see that putting the value over here is not the best design. That's why we need visitor. We'll get there. Okay, we'll get there. So now let's see, just focus on this. Given this, let's do a very quick warm-up. How do I create the tree structure like this? How many objects should I create? First of all, how many objects? 3, right? 341 as a constant object, 2 as a constant object, and then create an addition object, add a 2. Okay, let's do it very quickly. Of course, for the composite, you can also say we got something called add left, which will take some expression, and also we got another one which is called add right, which will also take some expression. Let's assume we also got that, okay? So what we can do is, let's do that quickly. You can say create, let me say, C1, C2 of type constants. And also we got A of type addition, like before. Okay, now how we declare them. So now we can say create the first object C1 dot make. And then we want to do 341. And let's create a second object here, C2 dot make of value 2. So let's add them up, okay? Add them up together to the root of the tree. So now we can say create A dot make. It will be up to your design choice. You can say for the make feature, I can directly pass C1 and C2. That's one way to go, okay? Or I can say after this, A dot add left. C1, A dot add right. C2. Okay? Just sketch of the idea. Now, how does it look like at the runtime? So C1 is pointing to some constants objects with the value 341. And C2 is also pointing to a constants objects with the value 2, right? So now, as opposed to the case before, where we simply got over here. So where did I put it? So where's that page? Did I put it somewhere? Oh, this over here, okay? As opposed to the case before, where the addition contains an array or list of children. Now it's not the case anymore, okay? What we have is something like this. What we have is something like, so now A, which is addition, is pointing to an addition object over here. And then it has left and right, okay? L for left, R for right. Left is pointing to here, C1. Right is pointing to C2. So now, how do I get the left operand? I can say A dot left, as opposed to A dot children at position 1. Right? To get it right, I can say A dot right. Let's adopt this design, like a variance of the composite pattern. But they're both composite. Okay? Any questions about this? Okay. So far, we haven't even talked about visitor yet, right? I'm just trying to somehow linking you to gradually move towards visitor. Okay, so now, if no question, I'm going to move a bit. That's what we have over here. So now, this is the problem. So now let's present the problem. You can see over there, as I said before, the value over here is one possible feature for expression. Let's say, for example, if I got 341 plus 2, like this, what should be the value for that? 343, right? Like how we calculated price before. There might be many more features or operation we'd like to support for this particular expression language, which supports constant and also addition. For example, we may want to do something called prefix printing. We may want to do something called postfix printing. We may want to do something like generate C code. For example, I'll show you. Just as a sketch, very quickly. Go ahead. What do you mean the result? Where? You mean the value over there? Yeah, if you say A the value, of course it should return. If you say A the value over here, if you say a dot value over here, that's exactly how we implemented the price feature previously for the equipments. So it's going to be adding 341 to 2, right? I'll leave the implementation to you, okay? So now here's the problem, okay? The problem is we are given this particular structure of the language, a very simple expression language. And here's the problem. The problem is we would like to support a variety of operations on the language. We may want to do evaluates, in which case, let's say A is represented by 341 plus 2. Okay, let's say that's the A object we talked about in the previous slide, right? That's the A that we talked about. If I say A dot evaluates, for example, that should give me 343, right? If I say A dot, let's say print prefix, that's like a prefix notation that we learned about before, right? It's going to be, for example, you can say plus and 341 and followed by 2. That's prefix notation. I can also say something like A dot print postfix, in which case I've got 341 and 2 and then plus, right? Different operation I would like to support. And later on, as we add in more operators for the composite, we can also do type check. So we can gradually build towards something like a compiler, gradually, right? That's kind of the potential for this particular expression language. So these are so many operations we may want to support. So now without really going into the details about how to implement those operations, how would you design them? Where should we put the features? Basically, we already got this language structure here following the composite pattern. That's good. How do we extend this pattern over here to support all these operations I just mentioned? Evaluates, print prefix, print postfix, and type check. Where should I put them? Which class should I put them? You say addition? Okay, let's say this. If you say either addition or composite, right? Let's say I put it in the composite, for example, right? Just say for one thing. If I say evaluates over here, if I put it in the composite over here, what does that mean? That means only the addition support the feature for evaluates, but can I evaluate 2? I cannot. I should be able to evaluate a constant, which would be just the value itself. I should be able to. So this is not the way to go if you only put evaluate over here. We should put the feature somewhere so that the P features will be inherited to all the descending classes for expression. So where should we put it? Expression. Okay, good. I'm glad you're all misled by me. That's not a good design. But let's do it first, okay? Let's try. Basically, what we are convinced somehow was to say, for example, I will put evaluates over here. Let me just do it again. And if I put evaluate over here in blue, question for you, should it be deferred or effective? Why can it not be effective?
Because it's on, there could be like another class could like somehow convert it.
Yeah, basically it cannot be effective. Effective means you know what to do for any expression, how to evaluate them. But expression can be of different kind. It can be addition, it can be constant. The way you evaluate addition versus constant will be different. So at this level, I simply don't know. So a good design for this case would be evaluate, make it deferred, and then let all the effective class, descendants class, inherit that. So that means over here, I got to say evaluates plus. Evaluates plus. Agree so far? Okay. Now, we can do the same. I'll use a different color. Do the same for print prefix. Defer over here. Print prefix also should be effective. Also, print prefix also one another color. Not about print postfix. And I will put print postfix over here and one more. Let's not worry about type check for now. That'll be enough to illustrate the idea. It should be effective over here. Right? That's kind of the design to handle the extension. Okay? Now, I claim that this design is bad. Why would you think that's bad? Really? What kind of redundancy do we have? Interestingly, the code or design does not smell in this particular bad design. So you cannot just apply what we say is bad before to here. So if I ask you about this, what's bad about this design? If you simply tell me this design smells, that's wrong. It doesn't smell. Okay. Huh? It's hard to, you mean it's bad, hard to maintain? What do you mean hard to maintain? If you only tell me hard to maintain, it's also not specific enough, right? You want to add a new feature to where? Okay, I can kind of see what you mean. Okay. One drawback for this, there are two drawbacks basically. One drawback is about violating the single choice principle. Okay, again, we'll talk about again single choice principle. What's single choice principle? If you, yeah, that means if you will violate the single choice principle if for a particular change, you're going to change in multiple places, right? Let's say for this particular design, let's say I want to add one more operation to handle the expression language. I want to say generate C code. Okay? I want to say something like this. I want to add basically, let me put a color green. A new feature generates C code. That's a simple change I want to make, which means given any expression, I want to generate the corresponding C code in the right C syntax, or generate Java code, or generate C# code, whatever, right? So now, how do I satisfy this particular change? How many places do you have to modify? Huh? In this particular case, how many places? 2, right? All the descendants for the expression, right? That means place number 1, I'm going to say generates C code, implemented over there. That's place number 1. And then generates C code plus number 2. So the multiple places. If I got 100 different syntactic components classes for expression, I'm going to change in 100 different places for this particular new operation. That's a very big drawback. It violates all the, it violates single choice principle very severely. Okay? There's simply too many classes you have to change.
Also, the constant needs to be carried from the constant too because it needs to navigate from left to right.
Not really. So the question was, well, actually no. The constant over here basically is like a basic components, right? So that means does not contain any subcomponents. So when you say evaluate, for example, you can just give the constant value. When you want to do prefix printing, just print that number, right? Okay. That's drawback number 1. It violates the single choice principle. Drawback number 2, okay? Nothing to do with the code duplicate or not. Again, there's no code duplicates. That's a good thing about this design, okay? The second thing is more about cohesion, okay? When you guys learn about 2031, what's the principle for Unix? I'm not sure if you learned about this phrase, huh? Everything is? Everything's a file? No, that's kind of superficial, but maybe you're right, yeah? Yeah, do one thing and do it well, okay? So now, let's extend this notion about do one thing, do it well to the context of object-oriented design. That means a single class should try to do everything related to a unifying theme. You shouldn't try to do a variety of stuff. In this case over here, we are really trying to do a variety of stuff over here. Because, for example, if you talk about over here, let me highlight it. For example, about generating the C code versus evaluates. They're basically 2 very different tasks, right? But we're putting them in the same class. That's something violating cohesion. Okay? I'll write it down. So these 2 features over here, not coherent. That means they do not belong to the single thing. the same thing. That's a second criticism for this design. So criticism number one, it actually violates the single choice principle whenever you want to introduce a new operation. And drawback number two, it pollutes all your classes over here by a variety of unrelated operations. It violates the cohesion principle. Okay?
Oh, Professor, you're saying that evaluate and JET-C code are not...
Well, I'm just saying one example would be, yeah, basically all the operation potentially you want to introduce to the expression class in the future might also be unrelated. So that means you got lots of unrelated stuff in a single class. That make your class like a Superman class, right? You don't want to try to handle everything in a single class. Okay? Guys, any question about this? Is it cohesion? What does plus mean? Guys, help him out. What does plus mean? Good. What does effective mean? Whatever the superclass will enter the class. All right? There you go. Okay? Yeah. The question part? Coherence. Yeah, let's go over a slide. I do have in the slide. I'm just trying to illustrate first before I go over that. Yeah, I'll get there. Yes, question. Can we still implement some feature in the deferred class? Yes. You can think about deferred class as like an abstract class in Java, in which case you can have a mix of implemented and unimplemented methods. Yes, you can. Yes. Okay, so now let's go over the two drawbacks. Okay, you can see the actual visitor pattern is actually very complicated, but we're going to understand why this feature, why this design here, even though intuitive, but it's very unmaintainable. Okay, let's go over the drawback once more. Okay, that's exactly what I drew. Okay, you got different features over there. So let's talk about the problem. First of all, single choice principle, right? So if you want to add, delete, modify operation, you want to go to all the descending classes for the expression. All the descendants, right? Multiple places. Also cohesion. This is also some guiding principle you should have for your class. For example, for lab number 3, should you put Sudoku game and also error reporting in the same class? You shouldn't. That also violates cohesion. You want to, because Sudoku game itself has nothing to do with error reporting. It should belong to another class. Yeah, which is some hint for you in case you are curious about it. Okay, a class is supposed to group relevant operations into a single place. Do one thing and do it well. Okay, and it's confusing to mix everything together. All right, and so what we want to avoid is to pollute your classes with everything that's unrelated. Okay, that's about the second one. Okay, guys, any question about this design here? After this, we'll introduce one more principle, and then we'll go to visitor. Okay? Yeah. Hilariously, we're almost running out of time. I haven't got to visitor yet, but we'll get there. Yeah.
So what's the point of different classes if like we have hundreds of inherited like classes which inherit from a different class? If they're all implemented.
Yeah, you can think about it. The question was, why do we need deferred class in this case, for example? Basically, deferred class gives you the flexibility of implementing some code that can be reused by all the descendant classes. At the same time, you can also put deferred features there, which also got a signature. And those signatures will constrain all the descendant classes to be forced to implement those features. We'll see exactly that in the visitor pattern again. Okay? Yeah. Okay, can you speak out a little bit, please? The dynamic type of A is? Well, the question was, what's the dynamic type for A over here? Well, it should be quite obvious, right? Because A was created over here using the make feature, right? So hopefully you know the answer, right? If you don't know the answer, maybe speak to me after class. We need to talk, all right? If you don't know. If you know, that's okay. All right. Let's talk about something called another principle we need. Another principle, okay? It's called open-close principle, okay? Abstractly speaking, briefly speaking, what does open-close principle means? That means your system must be open and closed at the same time. Sounds contradictory, right? To be more precise, you should, as for you as a designer, you should identify parts of the system to be open and parts of the system to be closed. What does it really mean for one part to be open? That means that part is subject to extension or change. What does it really mean for one part to be closed? That means you should really try to really change that. Or basically, that part shouldn't be changed. Okay? Conceptually, this is what you have. Okay? You can think, I'll just draw that very quickly and I'll use the example to explain to you. If you think about this is your system over here, like a box. So one part should be open and one part should be closed. And which part should be open, which part should be closed is completely up to your judgment. Okay? Now, the closed part means that part should be hidden. And we go back to information hiding, right? You should hide those parts that should be somehow hidden from the clients, right? So those parts should never be changed by any request by the clients. Okay? On the other hand, for the open part, that means if you want to extend your system, that would be the part to touch. Abstractly speaking, that's what the open-close principle means. Let's see one example. Okay? For this particular language expression example we have over here, so how can we apply the open-close principle? Okay? How many parts are there, really, conceptually, for this particular application? How many parts? Well, you're simply counting the number of classes, right? But we need something that's even more abstract. One part is about the structure of the language. The other part is about the operation of the language, right? Right? Like how I draw. Okay? So we got two parts over here. One part is about the structure, which is about all the four classes that we're talking about. One part is about the operations for the language, which can be type check, print the prefix, print the postfix, and then evaluates. Okay? These are the two parts. Now, how do we apply the open-close principle? Open-close principle tells us we should somehow determine if they should be both open, they should be both closed, one open, one closed, or vice versa. So there are four possibilities. Doesn't matter which one you go, but you gotta commit to whatever design choice you make. Okay? Let's just talk about two of the alternatives. Okay? Only one of them is applicable to the visitor pattern, which means if you go to the other one, that's not an application context for the visitor. Okay? Let's go over that very quickly. So now we talk about open-close principle over here. Let me just go over some slides very quickly. Okay? Open-close principle, if you are talking about extension, that should be the open part. And the closed part should be also, should not really try to make any modification to the closed part. So now when you try to extend something there, okay, only modify the open part and also do not modify the closed part, right? We already said that. You can also think about the open part is going to be unstable. It's subject to changes. The closed part is going to be stable. Yes?
What do you mean that, like if the code has a weakness, that would mean when you say not stable? We're talking about it being changed, so you said not stable?
Yeah. So basically, when I say stable, unstable over here, you can think about over here, unstable simply means you might make changes to that part for the extension. On the other hand, when I say stable over here, that simply means if you want to introduce any extension to your system, that's not a part to touch. That part should remain unchanged. This is a little bit abstract. How about this? Maybe let's see the example first, and then also see the visitor pattern. You can ask me again. Okay? Yeah. Okay, let's just go over that very quickly. So now, let's talk about our expression language. Okay? Let's talk, in order to apply the open-close principle, we got at least two possibilities. In theory, it should be four, right? Open, 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 close, close, open, close, close. Let's only talk about open, close, okay? One alternative would be, we can say that the structure of the language should be closed, and the language operation might be open. What does that mean to you, just by seeing the English? What does that mean?
That means we should never change, like, for example, create children or linked list, we shouldn't change that. Like, that should be closed.
Okay, you say children of the linked list. When you talk about linked list, you're talking more about runtime. Okay, let me give you a little bit hints. Okay, alternative number 1 over here, also you can see from the table. Okay, so now let me just see that. Okay, sorry that it's a little bit inconsistent with my number, so there should be alternative 2 on the table. Okay, let's look at this first. Let's focus on this. If I talk about this particular alternative over here, which means the structure of the language should be closed and the operation should be open. What does that really mean in terms of architecture over here? Which part can we change? Yep, so you can see, let's say, let me use pink over here. For the pink version over here, that means only the operations is open. That means I should really expect the language structure over here to be closed. That means I should really not introduce any element to the language structure. For example, if I try to introduce a multiplication, that means I'm going to add a subclass to the composite over here, right? That means it violates this particular open choice close decision. Okay, so that means if it is open, it will be okay for me to add a new operation to support. Okay, new operation could be, let's say, generate Java code. That would be a valid change to introduce. So that means this part here is exactly what is open. That would be okay. What about another alternative? Another alternative is over here saying that, let me use maybe green. Green is not good. How about orange? How about this alternative? It's exactly the opposite. That means based on our commitments, we want to make sure the structure can be open, but the operation must be closed. What does that mean? Before you ask the question, I would rather go with this discussion first. Okay? What does this row over here really mean? Okay. Yeah, that means in this alternative over here, we only want to have 1, 2, 3, 4 operations as we had. Evaluate, print prefix, print postfix, and type check. We don't want to add any more operations. On the other hand, we are okay to add maybe something like as a descendants. We can say now we want to add one more class, maybe called multiplication. So multiply and also effective, and that should be the subclass of these two. So that will be okay. So now you can see that I'm basically talking about making two possible changes, right? So now, how do we judge to see if this particular change violates the open-close decision we made before? You have to see which part should be open, which part should be closed. Let me summarize very quickly, and then I'll take your question. The open-close principle tells us you have to make a decision to say which part of your system should be closed, which part of your system should be open. So now let's talk about two possibilities. Possibility number one, we are saying that the structure should be closed. That means we don't expect to modify the structure of the language. That means if you try to make such multiplication introduction, that'll be violation for this particular open-close decision. On the other hand, you can definitely add a new operation like a generate Java code. That'll be okay, according to this particular decision. Okay? On the other hand, if our open-close decision was the other way, which was completely okay, in that case, we can say, like, and now in this case, the operation part should be closed. That means if you try to add a new class over here, that should be okay, that should be allowed, because the structure part is just open. On the other hand, having this new operation over here, since that's supposed to be closed, is not considered as okay, depending on which open-close decision you have made. Okay? Okay, any questions about this? Oh, you go ahead. Yeah.
So when we're talking about structure versus operation, structure is talking about the internal framework of the class.
Structure simply means the base case and recursive case structure for the language, right? So you got addition, you got constant, you may later on have multiplication, etc. Just the language structure itself.
Oh, so not just simply features.
No, structure here is simply structure of the language. So here, when I say structure here, is the structure of the expression language, the syntax. Because the way we design the syntax for this particular language, we say it might be a constant, it might be addition, right? Okay, that's what I meant by structure. And for operation, I simply meant what operation can we apply on this particular syntax.
So like composite gets implemented in our example by linked list.
Part of the implementation for the composite is linked list. Yes, part of it.
If I wanted to change that and structure is closed, that's not okay?
That simply means you are doing something wrong against your original decision,
Yeah,
right?
but like, remember when we did information hiding and let's say the client wants to switch from a linked list to an array and the
Yeah.
client, the supplier wants
Yeah.
to switch from a linked list.
I see what you mean. So basically, this open-close principle and information hiding principle is a little bit different, okay? So you basically got a little bit confused with, when we talk about information hiding, versus open-close principle. Okay, so these two are not really the same. Otherwise, they would have been considered the same principle, right? Information hiding simply say, from the client's point of view, whenever you try to make any changes internally, it should not affect the client's code. Okay, so for this say clients not affected by constantly changed design decision. Design. Okay, that's what information hiding is. For open-close principle, it's more from the supplier's point of view. To say, if I'm the supplier, now I want to think about which part of the system should be more about the part I should really make changes on. Nothing to do with clients. Okay, so let me just make it's a good question actually. So information hiding is more from the client's point of view. Open-close principle is more from the supplier's point of view. For you as a supplier, you want to make sure once you identify something as closed and something is open, you want to make sure that decision is kept, is respected consistently, right? Okay. You mean the open-close over here? Oh, you mean these are two alternatives? Yeah, you can have other alternatives as well. I'm just talking about these two as a. Huh? Oh, we'll get there. Yes, we'll get there. Yeah, we'll get there. Mm-hmm. Yeah.
Is there a way to define like the open-close structure, just like if the information hiding wouldn't put the none?
I would say try not to really mix open-close principle and information hiding together. They're kind of different. So they're kind of orthogonal. You don't think about their interleaving too much together. Think about, when you talk about information hiding, think more for your clients. What should they see? When you think about open-close principle, think more about your convenience as a supplier. When you make any changes for implementing the extension, which part should you change on your system? So orthogonal, okay, independent. Still a little bit abstract, but since we're in the third year, let's try to be sometimes learn principle from the abstract level. So now, back to your original question. Since we got two possible ways to make the design choices according to the open-close principle, only one of them is applicable for the visitor pattern. Okay? So now, the visitor pattern basically is very good for the design choice where the operation is open. Okay? Let me say that. Let me put it here. This blue part over here is, I'll put it here, that's the application context of visitor pattern. Which means if you somehow have an application where the operations are very limited, it should not be extended, and also the structure can be expanded as much as you like, that's not the place to use visitor pattern. Okay? But we haven't seen visitor pattern yet, but we'll get there. Okay? But there are much background information to be discussed before we can get there. Okay? Guys, any questions until now? I only got about 5 minutes, maybe. It's already 50? Oh, too bad. Okay. How about this? Okay, I will continue with this next Tuesday. Okay?